All right. So today I'm going to tell you a story about the electric transport in a dirty marginal Fermi liquid due to quantum interference. So before I start, I would like to thank the organizers for having me today, and also thank my collaborators, Yang Shen at CMTC, and also my advisor, Matt Foster. So in this conference, we have seen a lot of samples of strange metals, and one big mystery is that why do they exhibit linearity resistivity? This has been seen, for example, in cuprates, and the early proposal was that suppose we have a phenomenologically a marginal Fermi liquid, then perhaps we can get this linearity resistivity. But so far, we have no theory for this microscopic theory for this marginal Fermi liquid. But recently, we have some very exciting progress. So one big motivation to understand the strange metal phase is that potentially it is related to the origin of high temperature superconductivity. So if we have a theory to understand the strange metal physics, perhaps we have some new insight to understand the high temperature superconductivity. So in order to capture the effect of the quantum criticality, so we put forward a model with n flavor of fermions sitting on the Fermi surface coupled to SUN matrix bosons, which are essentially some magnetic connective modes. So we tune the bosons to quantum critical point so that the interaction mediated by them is long-ranged at 0 temperature. So this model is SUN symmetric, and at the large n limit, if we don't consider the effect of this order, the self-energies are well known. For the bosonic sector, it has a singular form like this, whereas for the fermions, it acquires a quasi-power 2/3, but so far, there's no disorder entering this model. Yet, in real materials, we know that disorder is inevitable, and especially if we are thinking about cuprates, the system can, in general, be quite dirty. So we are trying to introduce disorder to this model. So the type of disorder that we have in mind is on-site impurity potential disorder, which are Gaussian distributed. The disorder strength is essentially controlled by this elastic scattering rate gamma EL, which is assumed to be much smaller than the Fermi energy. Here, unlike the SYK model, the Yukawa coupling between the fermions and the bosons is kept constant instead of random. And we also introduce a quarter-bosonic interaction, which is symmetry allowed and analogous to some spin-spin interaction. So we use the saddle point equations to perform disorder averaging and to find the self-energies for the fermions and the bosons. So what we find is something very interesting, and disorder would drastically change the self-energies for the bosons and the fermions. For the bosonic sector, with disorder, right now the original clean self-energy is being modified to this form. The original singularity sitting at the denominator is now smeared out due to disorder, and the bosons essentially behave diffusively. And for the quarter interaction, it would introduce a thermal mass for the bosons, which is very general at finite temperature. So right now, the bosons acquires a quantum relaxational form, which is very generic. And if we consider the feedback of this quantum relaxational bosons to the fermions, then we, on top of the impurity scattering self-energy, we have a marginal Fermi liquid self-energy instead of the original 2/3 power. So here we see that this order actually plays a very important role and shouldn't be neglected, because they can modify drastically the self-energies. So, okay, so we right now have a theory to understand a possible origin for the marginal Fermi liquid self-energy, which was proposed almost 30 to 40 years ago. But that's not the end of the story, because when we consider transport, we consider the current correlation function, and we have to take into account the vertex corrections. And after doing that, we find that the marginal Fermi liquid actually doesn't give us anything new, because the linearity resistivity supposed to be there will be cancelled by this vertex correction. And this is not something crazy, because we know that in general the quasi-particle lifetime cannot be translated directly to the transport lifetime because of some backscattering effects and forward scattering effects. And in our theory, we'll try to check this again using the density response function. And a remark is that such cancellation is also seen in some recent paper in the Harvard group. All right, so everything right at this point are just basically semi-classical. So we can ask, do we see something interesting at the quantum interference level? So for impurities, we know that they can introduce inhomogeneous fluctuations in the single particle wave functions. And this can in turn generate some density oscillations around the impurities. When electrons scatter off these fractal oscillations and also interacting through each other via this quantum critical interaction, they can give us some oscillator one-off quantum corrections. In the Fermi liquid case, we know that the oscillator one-off correction is a localizing correction which has this logarithmic form and is singular at low temperature. So meaning that this correction can be important and shouldn't be neglected. The intuition here is that in the diffusive limit, because of this order, right now the electrons are basically performing random walk and move diffusively very slowly. So on average, they have more time to stay close together to interact with each other, and this can in turn enhance the interaction between them. So although in this case, the concept of quasi-particle is ill-defined because of the marginal Fermi liquid self-energy, the connective modes called the diffusion can still, describing the diffusive motion of electrons can still be well-defined. And the field theory description of this connective mode is called the Finkelstein nonlinear sigma model. So on top of the original Finkelstein action, we also acquire a correction due to the marginal Fermi liquid self-energy. And the propagator right now for the diffusion is anomalous because of the marginal Fermi liquid term. And speaking of interactions, we got two types of them. The first one is the Hayekemi box, and the second one is due to the Yukawa interaction. A technical note is that the second term here is not present in the original Finkelstein model, but it is important for fitting the Ward identity. So the diffusion is now anomalous, but they can't have practical consequences on the density response function because it has to satisfy charge conservation. So once we take into account impurity ladders and interaction ladders in the density response function, actually the marginal Fermi liquid self-energy got cancelled, and we are just basically recovering the Drude conductivity, which is consistent with what we do in using the current correlation function. So the more interesting effect is the quantum interference correction, which is what I mentioned before, the oscillator one-off correction. So upon summing all the diagrams responsible for the density response function, we obtain a relatively simple expression. So it has a thermal factor, and then some copies of the anomalous diffusion, and also the propagator for the quantum relaxational bosons. So this formula can be reduced to the Fermi liquid oscillator one-off formula, and the final result is something like this. So here I'm presenting the resistivity normalized by the Drude one. So there are a few terms. The first one is just the constant piece, which is the Drude one, and the second piece is the AA correction, which is so this is the conductance correction, which is inversely proportional to temperature. So at very low temperature, this piece is dominating and can give us a potential source for linearity resistivity. And the second ingredient here is inelastic scatterings, and but this is probably just Fermi liquid-like and cannot give us anything like strange metal. And importantly, this correction is anti-localizing, meaning that the perturbation theory that we are having is under better control as we go to lower temperature. And one easy way to understand the 1/T correction of the AA conductance is basically just due to the thermal mass, which is proportional to temperature in the bosonic propagator. And this can also be seen by just power content, basically, in this formula. So another important message here is that this AA correction cannot be cancelled by any vertex correction. And the existence of this AA correction means that although we don't have well-defined quasi-particle in this system, some kind of quantum phase coherence can still exist in the form of connective modes. And this is important because we know that phase coherence is necessary for superconductivity. So speaking of superconductivity, we have some preliminary results that I'd like to share with you. So first of all, superconductivity can potentially be enhanced because the critical interactions are strong and they can be very strong glue. Yet on the other hand, because of the concept of quasi-particle is now ill-defined and they die very quickly before they can form pairs. So this kind of Planckian dissipation can prevent the pair to form, and it's naturally pair breaking. Yet, a very interesting effect that we've found is that if we consider the interference between the couplons and the quantum critical interactions, we actually see an enhancement to the transition temperature. But we have a few competitions, and which one would win, we are still performing the calculation, and hopefully we can update you in the near future. All right, so with that, let me just put the summary here and comment on a few future directions. So we have seen that randomness can potentially play an important role in the strange metal materials. So perhaps one further experiment or further calculations that we can look into is some kind of mesoscopic effect. For example, conductance fluctuations and some spectral statistics due to sample-to-sample variation of the randomness. Yeah, with that, I'd like to thank you all for your attention.
So on the first part, it seems like this dichotomy between the relaxation rate and the conductivity is really crying out for the presence of a lattice and some kind of like short-range interaction, so that you have own part.
Right. So here we are considering a continuum model and instead of a lattice model. So in principle, we don't have club, and if we consider in a relatively, well, if the Fermi surface is not that large, then I would suppose unclubbed scattering across, across different Fermi surface would be suppressed. But yeah, here we are not considering unclubbed, and there's no way momentum can be relaxed without disorder in this scenario.
Hi, nice talk. For this to work, you need some gapless collective mode in the clean system, right?
So there are three ingredients. So we have fermions sitting on the Fermi surface. We have quantum critical bosons, which are gapless at 0 temperature. And finally, we have disorder. So disorder would have can introduce some impurity ladder dressing for the Feynman diagrams, and
So the gapless collective mode, so you're assuming you're at a quantum critical point, so it's a gapless collective.
Right, but at finite temperature,
It's a big assumption. That's fine.
but at finite temperature they can acquire a thermal mass.
That's actually crucial.
Yeah, which is
Which is actually very general. I have a big quantum critical point. Those articles are damned by thermal mass. And that's why it gets this linear resistivity. It's from the thermal mass of the organization.
Are there any more questions? All right. If not, I'd like to thank our speakers and TC again for the great